Hello, I'm Matthias Kerzel from the Knowledge Technology Group at the Department of Informatics from the University of Hamburg. I'm going to present joint work with Lara Mier, Eric Strahl and Stefan Wermter on a humanoid robot learning audiovisual classification by active exploration. In the past, we have worked with active object classification using the audio and haptic modalities. For the audio modality, a robot would, for instance, shake an object to find out what it is filled with. And in the haptic modality, a robot would squeeze an object to find out the material it is made of. What we learned is that exploration using something other than the visual modality is often active, but we also learned that one modality is sometimes not enough to distinguish objects. So while one object might look exactly like another object, only by lifting them up or squeezing them, we find out they're made from different materials. We wanted to address this by devising an active audio-visual perception, so that uses both modalities, and we took inspiration from infant or child-object interaction, but also on how animals explore objects, and that is by throwing them down or bouncing them against other objects to get an idea of what it sounds like, how the object moves, what might be the material. Our research questions are: can we endow our robot platform Nico with the ability to classify objects based on active audiovisual exploration? What is the best way to train a neural architecture for this task? And how does the classification accuracy depend on these different modalities or the combination? Especially, can we really show that combining the modalities is a benefit? This is our object set of 16 toy objects, ranging from very hard and dense rigid plastic to rubber, dense foam, lighter foam, styrofoam, and all kinds of plushy objects filled with different soft materials. These objects all have different haptic properties, so when compressing them or squeezing them, they feel a little bit different. But do they also behave differently in our audiovisual scenarios? That's what we want to find out. So we took Nico, our neural-inspired companion, a robot platform developed in our work group, equipped it with high-resolution cameras, microphones embedded into the 3D-printed ears, 30 degrees of freedom, of which we mostly used the arm and hand motors to throw down objects, a slope, and then we can record for the objects how does it sound and how does the object tumble and bounce down there. And this is how it looked in detail. Nico would get an object into its hand and then drop it down the slope, and some objects would roll, some would bounce, some would tumble, some would just slide down, and they all made slightly different sounds. Here you see Nico live during exploration. Now, we had to do some pre-processing. If you look at these 16 objects, they have different colors, different textures, so it would be very easily to distinguish them using vision. What we rather want to know is, can an underlying network learn to identify these objects by the way they move? So do they bounce? Do they slide? Do they deform? And for that, we take the difference of images, and we take 2 consecutive timestamps in black and white from our video stream. We subtract them from one another, and then we have a so-called difference of images, which only tells us where is a change in the image. So basically, where is something moving and also how it is moving. That way we can exclude the very prominent color and texture information and focus on the motion pattern. For the audio stream, we also had to do some pre-processing. We created spectrograms. We can see very nicely the object impact sound with multiple bounces here, but we also do see that the robotic arm causes a lot of ego noise. That's why we had to modify the dropping procedure in a way that the robot remains very still after the object is dropped, so not to create artifacts in the actual impact sound. Then we came up with neural architecture. We have 2 arms in this neural architecture, one for visual processing, one for audio processing. These arms are joined in a part for multimodal processing. Each of the arms is again based on convolution and pooling layer blocks. The input for the audio spectrogram is basically just one image, the spectrogram, and here for the visual processing we have a stack of images for the multiple frames. Both pooling blocks are followed by individual dense layers and then concatenated in the multimodal processing block, followed by dense layers, and then we have the output. What we can, of course, also do is take this output and attach it to one singular arm of the architecture and only train one modality. And that's exactly what we did. So we started by training only one modality, the audio modality in isolation and the visual modality in isolation, to establish a baseline. And then we tried different ways of training the network. If we train everything simultaneously from scratch, or if we want to take a pre-trained unimodal network arm and then fine-tune it in the entire setup, or even keep the weights fixed and tuning only the multimodal part. And these are our results. So if we use only the audio modality, we achieve an accuracy of about 60%. Some objects like the heavy blue banana make a very distinct sound. They're perfectly classified, as you can see here in the confusion matrix. Other objects like the orange carrot are basically classified near chance level. They're often mixed up with similar objects also made from plush, also having a similar shape, so resulting in a similar tumbling motion down the slope, and especially eliciting the same kind of sound. Now, if we look at the visual modality only, we achieve about 84%, so we do improve by just using visual. But we also see, and that is interesting for us, that some objects are not classified as good as they were in the audio modality. For instance, the blue banana here drops to 88%, while other objects are much better in the visual modality. The orange carrot goes up to 80%. Now, our big hope is that when we combine these two modalities, we can outperform each singular modality. So our first experiment was to train a network for the multimodal audiovisual classification from scratch. And we were a bit disappointed because we only achieved an accuracy of 82%. And we saw some objects even performed worse than they performed before in only one modality. So how could this be? Our hypothesis is that, well, some objects are very distinguished in one modality, and they're very similar in another modality, and then they might not be classified very well. This creates an error. The error is backpropagated through the entire network and changes both arms. So maybe one network might constantly receive some updates, one network arm, while actually it's not its fault that the object is not classified so well. But it's very difficult to analyze where exactly lies the problem. So what did we do? We took the pre-trained network arms, so the visual and the audio modality, and inserted them into the networks and then trained the entire network. And now we can see that the accuracy actually goes up to 87%. So we can show that there is some bonus from using two modalities and not just one. And when we take the pre-trained networks arms and fix their weights, and then only learn the multimodal fusion of these modalities, we even achieve 89%. So in summary, we can show that we have about a 5% gain over the more dominant visual modality if we use the pre-trained network arms and then learn to fuse this information between audio and visual modality.
It sounds like the yellow dice. It moves like the yellow dice. It probably is the yellow dice. It sounds like the yellow duck. It moves like the yellow duck. It probably is the yellow duck.
So here you saw Nico in action, classifying objects by dropping them down a slope. In summary, we contributed a novel robotic audio-visual dataset that, given our neural architecture, can really benefit from using audio and visual modality. We implemented this in a robotic setup with the exploration procedure, and it's robust enough to really be used as a demonstration of the multimodal fusion and its benefit of learning in two modalities. We also learned a bit about how we can use unimodal pre-training to enhance the learning of the multimodal architectures. In future work, we want to expand to more complex exploration procedures, especially targeting more modalities. We want to use object tracking and pose estimation instead of the difference of images to even abstract more from the actual object shapes. And we want to expand to more diverse and noisy environments. Thank you very much.